relativity is chapter 38.
No, still 37.
Still 37?
Yeah. We are still in chapter 37. Okay, I know, it doesn't seem to want to let go. Okay? But today we will start quantum mechanics. I do want to talk briefly about general relativity. And then we'll get into quantum mechanics. We'll start quantum mechanics. I know I'm behind based on what the schedule says. I will make it up in quantum mechanics. Okay, because I tend to cut out a lot of quantum mechanics. Mr. Ragdale, who's also teaching this class, he cuts out optics and then spends a lot of time in quantum mechanics. So if you feel robbed, go talk to Mr. Ragdale. You can talk to me too. I'll fill in the blanks for if you want. Our quantum mechanics won't be nearly as detailed as this. Okay, so last week I blew your brains a little bit, right? By showing you that E equals mc squared is the boring answer, right? We've got light having momentum and actually able to cause, right, rotation and impact and all that kind of stuff. So the question, how does something without mass have momentum, is kind of like the wrong question, right? The right question is, what do we not understand about the universe because we've now proven it? So Albert Einstein developed all of that in 1905, while working as a patent clerk. And he knew it was severely limited because the special in special relativity means no acceleration. And come on, everything accelerates. Like you can't get something moving without acceleration. So he knew he had to do more due diligence. And so from 1905 until I think it was 1917, 15, 17. I didn't write down the date for when he published. But people read his papers and didn't understand what he was talking about, thought it was philosophical rather than physics. And Einstein would work for the next 10 years, 10 to 12 years, formulating general relativity, a relativity that would account for accelerating frames of reference and all that sort of thing. And as he did so, he realized that he needed to develop a new way of thinking about space-time. Not space and time, which is typically how we think about it in classical physics, but space-time, the fabric of the cosmos, the stage on which everything in the universe takes place. He developed this, and again, people still didn't understand really what he was talking about or why he was doing it. There was no real experiments yet that could be done to show that his special relativity or his general relativity were actually real. So we will, like we did with special relativity, we'll start a very theoretical basis and develop, start with first principles and then develop the implications, and then I will tell you the actual, I've already told you some of the actual experiments that are done to show that it's true. Okay, so we are working from a point of view where we know this is how the universe works. But Albert Einstein was coming at it from the other direction. So he starts with a principle. Right, like special relativity, there was those two founding principles. In special relativity, it was that the laws of physics are the same for everybody in all non-accelerating frames of reference, and that the speed of light is the same for all observers. So in the general relativity, Einstein assumes this principle. We call it the principle of equivalence nowadays. Okay? And the principle of equivalence on the surface kind of seems, well, duh. Like, I don't know, right? But again, Einstein is insisting on something and then is going to try to discover what the implications of this insistence are. So let me see if I can help you understand the principle of equivalence. I have a ball and I drop it, what's it going to do? Good what? Bounce, fall. Okay, so first, before it bounces, what's it going to do? It's going to accelerate, right? Okay, it's going to change its speed. It's going to go from zero speed and get faster and faster and faster until the floor gets into the way. Why? Because gravity pulled on it. Okay. Gravity is a force. Albert Einstein is saying we can't tell the difference between the force of gravity pulling that ball down and our frame of reference being accelerated upwards at 9.8 meters per second squared. Okay, now Einstein's smoking something, right? Because obviously this room is not accelerating upwards at 9.8 meters per second squared. Right? So, Albert Einstein sets this principle and then tries to discover its implications. Okay? So, let's imagine, we're not going to do this, but we close the doors. We cut off all ability to measure what's going on in the rest of the universe, right? All we know about is what's going on inside the classroom. Okay? And we do an experiment, right? We let go of a ball. One way to describe why the ball falls is to say that there's a gravitational field, right? Force pulls it down. An equally valid and untestable conclusion is to say that our frame of reference, our lab, is being accelerated upwards at 9.8 meters per second. That's the principle of equivalence. We can't tell the difference between a gravitational field and an accelerating frame of reference. Again, because our lab is cut off from being able to measure what else is going on in the universe, this has to be true. So, let me show you this. Where did I put it? Oh, did I get rid of it? Of course, I very cleverly had it all set and ready to go, and then I closed the window. Where did it go? All right, there. Let me show you relativistic space sheet. This was made by Henry Wright, the Minute Physics YouTuber. Okay, made this little website to try and explain relativity, general relativity, to students of physics. So I'm not sure why the sheep are there. Henry Reich has a thing for sheep and his whatever. Okay, so I'm going to get rid of the sheep. Okay, and so you can see here that we've got a rocket ship, and there is like a water dropper, right, that's shooting beads of water just horizontally. And since this rocket ship is in space, right, and there's no gravitational fields anywhere, right, we would just see the water droplets go sideways. And what we've got is a picture of the rocket ship in the frame of reference of, say, the universe, and then we've got a picture over here of, like, from inside the rocket ship's point of view, where it can't see the rest of the universe. And what I'm going to do is I'm going to accelerate the rocket ship up. Okay? As long as I'm holding down the accelerate button, do you see how inside the rocket ship we would see the drops of water land in this regular parabolic? What happens as soon as I let go of the acceleration? It's back to the weightless version. Now, is it moving? Yeah, but it's not about motion, right? It's about acceleration. Okay? So let me put the brakes on here. Stop. Okay? Sort of a reset, right? So again, we can't tell the difference between a gravitational field, which would be the box over here, versus a frame of reference that is undergoing acceleration. That's the whole underlying idea of Einstein's principle of equivalence for general relativity. There's no physics experiment that can be done to distinguish between these two different, unique sets of physics, right? And if you just go search for relativistic space sheet, you can find this. I'll put the sheet back. Okay, and then we see the sheet will go all over the place, depending on which way you accelerate your rocket ship, and you can go that way. You don't have to just go linearly. But anyway, sheep tumble around. No sheep are harmed. I think some physicists and some coders were, but no sheep were harmed in the creation of that. Yes?
So is that the reason why on those, like, I don't want to say anti-gravity, but where they take the plane and they'll dive and you can simulate some
Yeah.
gravity?
Yeah.
Same reason?
Same reason, right? Well, the plane is falling
Yeah.
at the same rate that you would in free fall, and so there's no need for normal forces. Yeah, it's frames of reference trickery. Just on the plane, you got to make sure you miss the ground. Okay, so what are the implications of this principle, right? How do we break the principle of equivalence? Well, the answer is, okay, what happens if you do it with light? Instead of drops of water, we take a laser beam and we shoot it across the lab, right? Light doesn't have any mass. So, if general relativity is wrong, the light beam should just do what? Take a straight path regardless of what's going on, right? Or, to turn the argument around on itself. If the principle of equivalence is true, you can't tell the difference between a gravitational field and an accelerating frame of reference, then light should be bent by gravity. Obviously, the Earth is not accelerating somewhere, right? I mean, it's going around the sun and all that sort of stuff, but it's like we know that the acceleration that's given to all objects in free fall is because of this force of gravity. So, if we're turning the argument around, then it should be that the Earth's gravity bends light. That's a measurable thing, isn't it? If we take a laser beam, we can see whether or not that laser beam is being deflected. So before we get to the actual experiments, let's talk about the principle of equivalence and this sort of weird setup where we can't see anything outside of our frame of reference, right? We're deliberately removing the ability to know if we are accelerating or not, right? So if we're in an elevator and we have a flashlight or a laser beam, right, and that elevator is accelerating with enough magnitude so that we could see the light bend, then we should see the light bend in that elevator. Like as the elevator accelerates upwards, the laser beam would leave one side, and by the time the laser beam got to the other side, the elevator would have accelerated upwards and changed its position. And so from inside the elevator, we would see the beam arcing or dipping. Okay? Principle of equivalence says it doesn't matter if we do it in an accelerating elevator or we do it next to a planet that has a gravitational field. We can't tell the difference. We would run the experiment, whether we are in an accelerating frame of reference or on the surface of a planet, and we would not be able to tell the difference between those two experiments. We would see the same results. Okay? So, I got some more, much cornier animation. I did not make these, somebody else made these. Okay? But I think in their simplicity and their corniness, okay, they're going to help you see the principle of equivalence in all of its glory. In both of these cases, we have a red object moving along a line. One of these pictures is the accelerated frame of reference, and the other is the gravitational field one. Okay? And we're going to play an animation. I'm going to play these over and over again, but just based on what you saw there, which one of these is the accelerated frame of reference and which one of them is the gravitational field? The one on the left is what? Accelerated frame of reference. You can see the frame of reference going up, right? The ball just moves along in a straight line, right? Newton's first law. An object in motion will stay in motion, right? Okay? So, if you look carefully, you might be able to convince yourself that if you were standing in this box that's being accelerated upwards, you would see that over there. Yes or no? Okay? That's the principle of equivalence. You can't tell the difference between an accelerating frame of reference and one in which there's a gravitational field. Okay. The object, the ball, is moving how? Along a line, obeying the law of inertia. It's the frame of reference that gives us the overall motion, right? If we were on Earth, we would say the ball takes a parabolic path. And why does it take a parabolic path? Because gravity is pulling it out of its straight line motion. Newton's first law says it wants to go, but we have a force that applies and so therefore causes it, pulls it into the parabolic path. But it is equally as valid to say that any ball that is being thrown and follows a parabolic path is moving in a straight line and we are accelerating upwards to meet it. Saw it all in your face. Saw it all in your face. Mr. Balogh, that is BS. Right? You can't tell me, Mr. Balogh, I woke up this morning and I know there was a gravitational field because I had to fight against it. I had to get out of bed. You're not telling me that my bed was in constant motion and it is accelerating, blah, 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 blah. No, gravity pulled me down. And my evil alarm clock woke me up.
Bed didn't want you to leave.
Yeah, bed didn't want you to, right? I suspect that the gravitational constant changes its magnitude overnight. It's much bigger in the morning, right? But again, accelerated frame of reference or gravitational field, you can't tell the difference. Now, this is the one where there's like a gravitational field, right? Okay. So if you were inside that thing, what would you see?
Straight line.
You would say there would be no gravity, which is where these zero-G flights come in. When the people ride on the airplane and they float around, okay? Why are astronauts weightless in the International Space Station? They're falling at the same rate that the International Space Station is falling at. They're in an accelerated frame of reference. But it looks to be motionless. This is the argument that Albert Einstein is making. You can't tell the difference. The laws of physics aren't stipulated well enough to be able to tell the difference between an accelerated frame of reference or a gravitational field. So if it happens with objects, the counter-argument is that it should happen with light. And so Albert Einstein struck out in an attempt, not like struck out 3 strikes and you're out, but like he struck out in a direction to try to figure out how this could be the case. What are the implications if this is true? And over a period of 10 to 12 years, developed a idea of what space and time were. The actual stage upon which we measure things. What does it mean to have place in the universe? What does it mean? What is time? And how does it flow? He already knew that time and space were up for grabs because of special relativity. But really, when you come down to it, what does it mean for space and time to work together? And he developed in this process a concept of space-time, not a physical thing, but really the reality upon which our universe is built. And it was like a fabric, It's a four-dimensional fabric. It was like a fabric that could stretch and pull and be kinked, and all of the things that we talk about gravity acting on things, could be explained by curvatures in space and time. So ultimately, what Albert Einstein is trying to say, that force of gravity, the one that you've come to know, rely on, hate, especially when you tripped in front of that person that you were trying to impress. Doesn't exist. Because it's not unique. There isn't a singular instance where you can show that gravity is the only way to explain what's going on. You can explain it from the point of view of an accelerating frame of reference. And so Albert Einstein, being Albert Einstein, said that's not good, and it can have two ways to say the same thing. So what is the way in which both of those things fit together? What's the third choice? The third choice is space-time. So, why does this ball fall? Because it follows the curves in space-time. That sucks. That doesn't feel good, right? That isn't what we taught you in Physics 4a, right? So, did we lie to you all through Physics 4a? Yeah, we did. But it's a good lie. We don't need to know how space-time curves in order to get from here to the moon. We don't. We do need to know how it curves when we do our GPS satellites. But to get to anywhere in the solar system, you don't need general relativity. So what's its utility? Why? How do we know it exists and all that kind of stuff? And why is Albert Einstein so famous? Einstein needs a way to convince the scientific establishment that gravity isn't real, right? Or can't be explained the way we think of it in classical mechanics. And so he really only has one laboratory. He doesn't have lasers will not be invented until the 1960s. The lasers aren't even a thing, right? So all he has are beams of light that he can play around with. And let's face it, stuff is going on the surface of the planet Earth just isn't happening fast enough to be like, he goes and calculates the gravitational field he would need in order to bend a beam of light. And he figures out that he needs something that is something like Jupiter doesn't cut it, right? He needs something that's like 1,000,000 times more massive than Jupiter. I wonder if there's anything around that's 1,000,000. Oh, the sun? The sun has enough mass to bend light. But what light would be bent by the sun? The sun gives off light. Stars? We go outside right now, we look up at the sun. Don't do this. Would we see any stars? No. Are they there? Yes. Why are they gone? Sun too bright. Okay? So how do you look at stars? They have to be near the sun, because the light coming from the star would have to be near the sun. But if the sun's too bright, how are we ever going to see the light?
Different wavelengths than the sun.
Okay, so here's the problem, right? So like we've got Earth, and we've got the sun. And we know it's the sun because it's spiky. Okay? And then let's say there's a star, and it's like the sun's in the way, right? What Albert Einstein has figured out is he can calculate the path that the light takes around the sun. If general relativity is correct, and he knows that space-time being bent by the sun's mass would curve the light coming towards the Earth, then what we would see from the Earth is this star moved out of its correct position. Again, we would see the light, we would follow the light straight back. The star would appear over here even though we know it's behind the sun. The problem is the sun is too bright to be able to see this effect happen. So how do you fix it?
Black hole.
Black hole. That's a bit extreme.
You could use the same principle that you guys used when you were making that electromagnetic telescope.
Yeah, Einstein didn't have that back then.
You didn't even have anything to try to look at different wavelengths.
Nope. Simpler than that.
Wait for an eclipse.
Wait for an eclipse. Now, I'm not going to pretend, right, that I know the answer to the thing I'm about to posit, okay? We happen to live on a planet whose... There's no existential there, real quick. We happen to live on a planet where, continue my thought, our satellite, our moon, is at the right distance and is the correct size so that when it passes between us and our star, it completely blocks out the star while still revealing the outer edges of our star. I don't know what you believe in, but that's a big coincidence. But it's one that humanity can use over and over and over again to our advantage. This doesn't happen on other planets. You go to Mars, there's eclipses all the time. But Mars's moons are like little captured asteroids, right? They don't block out the sun. Okay? Jupiter's got like 100 and something moons now. None of them cause full eclipses on the surface, right? Like it's just, our planet is special. It's special in a lot of different ways. And that's just one way in which it is special. So Einstein's going to take advantage of this feature of our planet's eclipses. I feel sorry for the other aliens. I really do. Because if they don't live on a planet, then they're going to have trouble. So this is from a newspaper in 1919. It's an illustration out of a London newspaper in 1919. The Illustrated London News. Okay? November 22nd, 1919. And it is an illustration that was put in the newspaper to help people understand exactly what was happening. In 1917, so 3 years prior to when this was published, Albert Einstein had been working with the scientific community, and an eclipse was coming up in 1917 that was going to be visible from the British Isles. Nice place, because British Isles had a lot of observatories and a lot of astronomers. Okay? And so all the astronomers, so Albert Einstein's working with these astronomers, and he's trying to say, look, I've got this theory, and I need you to measure apparent positions of the stars, blah, 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 blah. And in 1917, I'm sorry, I got my stories back. 1918, he's working with these things. It was cloudy. Kind of puts a bummer on being able to watch the eclipse. Okay? In 1917, there was a different eclipse that was taking place, but this eclipse was taking place in kind of like Poland into modern day, all the stands that are down there, Tajikistan and Turkmenistan and all the stands that are down there. But what was going on in 1917 that was kind of important? World War I. Okay? So a German team of astronomers left Berlin before the outbreak of war. So maybe my date's a little bit wrong. Maybe this is 1915. Doesn't matter. What I know is that they left Berlin 6 weeks before the eclipse was supposed to happen because they have to haul all of their equipment. They were in Tsarist Russia. Like the Bolsheviks were kind of doing their thing and all that sort of stuff. But they had crossed over into Russia. And were on their way to the place where the eclipse was supposed to happen when war broke out. Archduke Ferdinand, blah, 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 all that stuff, right? They don't know war has started. They're in the middle of nowhere, Russia, in the steppes of Russia. And a Russian unit of military captures them. They speak German, and they have a wagon full of telescopes. And war has just broken out between Germany and everybody else. The scientists end up in the gulag, okay? Right? And they're like, we swear, right? We're just here for an eclipse, we're in war, whatever. They end up in the gulag, okay? Einstein and the rest of the scientific community for the next 2 years are working to secure the release of these prisoners, right? And they do. They eventually do secure the release and they get them back home, right? Okay. But it kind of, war messed up the first measurement. Cloudy skies messed up the second one. There was like a third measurement, I think, and it was Hubble, Edmund Hubble here in the United States, and said, I'll go up to Vancouver, Washington, cloudy again. So 1919, it finally happened. An eclipse where scientists didn't have cloudy skies, they had their telescopes and everything ready to measure, and they went and measured the apparent shift, of a star around the edge of the sun, and the change in apparent position of the star exactly matched Albert Einstein's calculations. Where we need to be. And it was this moment in time that Albert Einstein went from being a nobody to being Albert Einstein. There's a reason he is a pop culture figure, and it's this date, and it's this time, and it's this experiment. I once heard that it takes about 10 years to become an overnight success. That's exactly what happened to Albert Einstein. He gets catapulted into the ranks of the famous. A man who's able to recast our understanding of how the physical universe works and prove it through experiment on the grandest of scales. And this date, we're only just barely beginning to realize that the universe exists. Like, prior to this, we don't even know how he hasn't yet done the calculations. He's just starting them to figure out that the nebula that he's looking at are actually different galaxies. We thought there was really only one, and we pretty much were only sure it was just our solar system. Like, it's hard to imagine, based on what we know now, how limited their understanding of how the universe worked back then. And Albert Einstein is able to rewrite our understanding of it. And not only that, predict something that we can measure. There's something else called the precession of the perihelion of Mercury. This gets a little bit into the weeds, but Mercury does not have an orbit that is correct according to Newton. If you use Newton's laws and Kepler's laws to predict the orbit of Mercury, you will fail. It just isn't right. Albert Einstein was able to figure out that it was space-time being warped by the sun's mass that was causing perturbations in Mercury's orbit, and his calculations exactly matched those perturbations. So it's like this, and then another, and then there was just more and more of these evidences that space-time is the real deal. So what's going on here? This video doesn't have any sound to it. I stripped the sound out, okay? Because he's a physics professor and he's a little bit long-winded, right? But you can see here that he's taken like this sheet and he's kind of bent it out of shape with a mass. He's rolling that ball bearing around. So this is a complete lie. This is not how space-time works. But it's about the only visualization we have that we can do in three-dimensional space. Because in four-dimensional space-time, any mass perturbs it in the fifth dimension. Okay? Right? But let's pretend the universe is a flat sheet, and then you place the sun in it, and you have that mass bending space-time. Any object, say a planet, that wants to move near this warped space-time is going to follow what kind of path? What does the Earth do around the sun? It orbits. Why? Good. You didn't say because gravity. Because gravity isn't a thing anymore. Gravity doesn't exist according to Albert Einstein. So how do you make the Earth? Why does the Earth go around in a circle? Well, it doesn't. The Earth obeys the laws of physics just like anybody else does. The Earth is moving in a straight line in curved space. But really, Mr. Balogh, is that really what's happening? Yes! And you do it every single day. When you go from wherever you live to here. Some of you are like, I live here, Mr. Balogh. I never leave this place. I can't get out. When you go from wherever you live to here, do you move in a straight line? No. And I'm not talking about you have to take a left in here and a right here, right? We got rid of all the buildings, right? And we just moved you along the surface of the planet to this point. Would you be moving in a straight line? No. You'd be moving in a curve. You take straight lines in curved space every day. Airplanes do it every day. If an airplane flew from San Francisco in a straight line to New York, what direction would it go? East is that way. So what direction to fly in a straight line to New York would the plane have to go? That way. Why that way? Because the straight line point between San Francisco and New York is through the planet. Got no worky. You have to fly around the curve of the planet. So it's really no stretch for Earth to be moving in a straight line in curved space. From our point of view, from our insistence on Cartesian coordinates, it looks like a circle. But space-time has been warped by the sun's mass. Why does the moon orbit the Earth? It doesn't. The moon is moving in a straight line in the curved space being caused by the Earth. Why does the International Space Station, why did GPS satellite? They follow the basic laws of physics in whatever local space-time they happen to be experiencing. This is an atomic clock. Again, we go back to time, right? Highly sensitive measurements of time. This is a GPS satellite that has an atomic clock in it. Every GPS satellite has an atomic clock on board. Okay? And a satellite, minding its own business, moving in a straight line in curved space, experiences different time than those atomic clocks sitting here on the surface of Earth. Because space-time is differently warped for them than it is for us. And so you make those corrections to bring the accuracy up of the constellation. It's these kinds of corrections, right, that are necessary from general relativity that bring GPS to its high state of accuracy so that my phone can tell me, well, you're an idiot and you forgot to turn here. Phones don't do that, right? GPS units used to, the little Garmin things, right? And it was a little passive-aggressive, recalculating, as I always say. When you missed your turn, it would say, recalculating. And I kind of just always imagined the poor woman that's trapped in that box, right? Recalculating for the fourth time. I read a funny story. This is absolutely true. The first in-car GPS navigation systems that were installed in Europe and Germany, there was a spate of accidents that were happening in Germany when drivers would run their cars into buildings. And it came down to the GPS units were telling drivers to turn. And what does the GPS unit usually do? Like you're coming up to the turn.
They tell you before.
They didn't used to tell you the distance, but they always told you before. And so drivers in Germany, hearing an instruction, would obey instruction.
But you don't see a building yet?
The GPS unit said turn, so you turn. I thought this has to be a lie. This has to be an April Fool's joke. This has to be some racist attack against Germans. I'm not sure how you do that. But anyway, I went in and I looked at it. No, psychologists were studying this. Like, there was a problem in the German psyche that if you are told by a voice of authority to do something, you do it. And it was mostly East German. Or former East German. Right? Because by then Germany had been unified. Just like a fascinating window into the psychology of a population, right? When they've been under such strict regime for so long. Anyway, GPS. But there's more. But wait, there's more. This is a Hubble Space Telescope picture. You can always tell because they're labeled HST. So I don't know if you can see it, but do you see the thin, wispy, sort of curvy things in this picture? Okay? I love all the scientific vocabulary I get to use now that I have a master's degree. Those filaments that you are seeing are not actual physical structures. They are the same thing that is behind those ultra-bright, fuzzy quasars that are in the foreground. So, what we have here today is a galaxy or quasar right there. And these images are of an object that's behind this one. And the light from that further distant object is being warped or bent around this supermassive galaxy that's in between us and it. And so we get to see the outer parts. This is actual photographic evidence that the universe obeys general relativity. Because without general relativity, we wouldn't be able to understand why these false color things in blue, this is a false color image. Everything in blue is coming from the same object. It's just that object happens to be behind this collection of stars. It's called gravitational lensing. This is my favorite gravitational lens. Okay? These four images are the same thing, but sit behind that thing in the middle. There's only one thing in this image, the bright thing in the middle. These four things are from a star that's behind that one. So that you can understand what a gravitational lens does, I want to show you some simulations. Okay, so this is not real. But what if we dropped a gravitational lens between us and, say, the Smithsonian, right? So we're standing here looking at the Smithsonian building, and I plop a gravitational lens right in front of us. So this is the accurate calculations for what it would look like if we stuck a massive object between, an object with enough mass to bend space-time a lot. Okay? So actual supercomputer calculations of what we would see because of a massive object between us and that building. You can see it's not what you predicted. It's probably not what you would even see if you were on certain illegal substances. Right? You don't need those substances if you have physics. Who knew there was a hole in the Matterhorn? And then, of course, you really can't talk about general relativity unless you talk about black holes, right? Okay. Black holes being this structure that is so massive that it warps space-time to a point of infinite steepness, infinite curvature, if you want to think of it that way. And so therefore, light trying to get out of the curve or the well or the deep can't. Often it's said that the curvature space-time, like black holes warp space-time so much that light can't even escape, or that the escape velocity of a black hole is higher than the speed of light, so therefore light can't get out, right? Those are all different ways of saying the same thing. Black holes break space-time. And they break it in incredible ways. Black holes were first calculated in the trenches of World War II by a German physicist who got bored calculating artillery trajectories and started playing around with Albert Einstein's equations and realized that there was a singularity, a point at which you could have enough density so that you could essentially break the fabric of space-time. What I've got here is a supercomputer simulation of what it would look like to approach a black hole. You'll notice there's a lot of light. That's because there's a lot of material that gets drawn towards a black hole. Black holes feed on stars and gas and that sort of stuff. And so you would see these swirling patterns as the material not only is in orbit around the black hole, but you'll see counter rotation. You see rotation one way and counter rotation the other way as space-time gets warped and pulled and stretched, not only by the mass of the black hole, but the rotation of the black hole. And as we get closer and closer to this thing called the event horizon, the point of no return of the black hole, the rest of the universe starts to get looking flatter and flatter and flatter, and brighter and brighter and brighter, until you get to the event horizon, in which case you've hit a point of basically infinite brightness. Like the event horizon marks the outer radius of a black hole, between the dividing line between where light and matter and stuff can still get out and where light and matter and everything else are trapped inside. And it's, have physicists calculated what it's like in there? Yes, okay. But practically speaking, you would hit a firewall, a literal wall of fire of all the material that's trying to get out of the black hole and can't. Everything that the black hole has consumed, everything that's been pulled in through that event horizon is piling up at that point. And so it's incredibly hot. We're like beyond star, like interior star hot. So that's first problem, okay? Second problem is that the gravity stresses are so big on you that there'll be a tidal force across your body. So tidal forces right now make the tides go up and down on the surface of planet Earth. Well, imagine a tidal force that was so big that you would experience tides across your body. And as you got closer and closer to the center of the black hole, you would literally be ripped apart atom by atom because of the tidal force across you. Physicists have a term for this. This is actually true. I am not kidding. It's called spaghettification. Because you are literally thinned and stretched out by the tidal forces that are acting on you. Okay? So you can conjecture, well, if I could get some unobtainium or something like that and protect myself from the heat and the tidal force, what would it look like? Well, we don't know what happens at the center. We do know what happens at the event horizon. Okay? And we do know the tidal forces. Their tidal forces are extreme on the outside, but they're extreme on the inside. If you were watching a buddy fall into the black hole, okay, then what you would witness is your buddy falling into the black hole, and as if they reach the event horizon, you would see them stop. As they get closer and closer to the event horizon, time slows down, according to you, and they get to the event horizon, and that's where time infinitely dilates. So you would never see them actually enter the black hole. They would be forever frozen, according to you, at the surface of the black hole. For them, looking out at you, they would see the rest of the universe come to a stop. I'm not in charge. So this is an animation of a stationary black hole. What it would look like if you were approaching a black hole, getting closer and closer to it. Again, supercomputer simulation of what it would look like to approach that black hole. You notice that it started circular, right? But as we get closer and closer and closer, the warping of space-time becomes greater and greater and greater. And eventually when we get to the event horizon, the rest of the universe turns into a ring around us. Okay? But stationary black holes don't exist. Stationary black holes are mathematical constructs. Every black hole, as far as we can tell, is a rotating black hole. It has some sort of angular momentum associated with its creation, and so it's spinning. And as that black hole rotates, we're not getting any closer to this one. Let's say we're just in orbit around it. This is possibly something that we would see. Do you see how there's counter-rotating bands around that black hole? Time actually runs in reverse for some of those counter-rotating things, okay? And things just get very weird. things get very weird around rotating black holes. And I'm not an expert in this. I was an optical physicist. I wasn't a theorist, right? I didn't do cosmology. We'd have to go get go pin down Mr. Ragsdale. Go pin down Mr. Trelawney, because they do have their degrees in astrophysics and theory. Okay, they can definitely steer you better. Okay, just a little simulation of what would happen if a black hole came between us and the Earth. Kind of what the lensing would look like, okay, if that were the case. Again, not practical, but just fun simulations, right, of what it would be like for that to happen. And then there were gravity waves, okay? So September 2015, LIGO, right, is able to capture the merger, okay, between two black holes. Again, supercomputer simulation of what it would look like for these black holes to be rotating around each other. As they rotate around each other and come into contact, they spin faster and faster and faster. This simulation isn't doing it. But then in the merger, they let off a gargantuan amount of energy, and that energy is expressed in ripples in space-time. Oh, they did coalesce. Good. Okay? Ripples in space-time, gravity waves. These are waves in space-time. Like without general relativity, we have no way to understand what a gravity wave is. And we now have 6 observatories that on a daily basis measure gravity wave occurrences. General relativity is real. You can't get away from it. What you have to do, what you're forced to do, unless you just want to, I don't know, go become an art major, is you have to come to grips with it and with what our universe is about. Atlas.
So that's the only way that gravity waves occur, is when two black holes meet.
Actually, just last month, LIGO thinks that they observed the merger between 2 neutron stars. They've been upping the resolution, for lack of a better word, the sensitivity of the gravity wave observatories, and now they think they've resolved the merger of 2 neutron stars, which are like several orders of magnitude less energetic than the merger of black holes. It's completely opened up a new way of being able to measure what's going on in the universe. James Webb Space Telescope, so the Hubble Space Telescope was able to get us back to about like 100 million, 200, 300 million years after the Big Bang in terms of like being able to look back in time. James Webb Space Telescope has pushed that to about 400,000 years after the Big Bang, just because of its resolution, its ability to see the infrared, all these other things. Gravity wave astronomy pushes us beyond that visible boundary. So what they're looking for now is the gravity wave signature of the Big Bang.
And what stage of the universe now is it?
And we're gonna find it. We're gonna find it.
We just don't.
Okay? Simply a question of when.
Didn't they just get an image, like a high res, well, as high as we can get of the black holes in our universe?
So last week what happened was they fed the data back through a machine learning algorithm to help sort of clean up the data and get a better representation of what it was, and they basically were able to get a higher resolution picture. It's a bit of a cheat.
Okay.
It's a good cheat, but it's still cheap. Okay. That was the end of chapter 37. Okay, it starts going pretty fast now, actually, okay? Because it's quantum mechanics, and I get a little bit bored. Bored's the wrong word. Terrified would be the more popular word. And I tend to go fast when I'm scared. So we're going to talk about a few things that are going to sound very in left field. Like, where did this come from? It all comes together, I promise. Okay. Speaking of Germans, a lot of stuff going on in Germany. This is Max Planck. Okay. Max Planck was a experimental physicist. They're all sort of experimentalists and theorists at the time, who in 1903 was studying something called black body radiation. Now, this is the same Max Planck after which the Max Planck Institute is named. The Max Planck Institute, if you're not aware, is like one of the premier research organizations in the world. Like, doctors, medical physicists, chemists, everybody goes, it's like the Marie Curie Institute in France. Like, it's huge, okay? So, big deal, Max Planck, that guy. But at the time, he's kind of not really, he's kind of known, like, in circles in physics, he's known as a good experimentalist. And what he's doing is he's dealing with something called black body radiation. That's a catch-all term for a black body is an idealized source of light. It gives off every wavelength in the spectrum. And so he's trying to study these black bodies. And of course, there's no such thing as an ideal emitter in the universe. And so he's using the next best thing, which is a really, really hot oven. I know that sounds weird, right? But what he's doing is he's heating up stuff. I know this isn't an oven, but this is an electric coil on a stove. And as you turn on the electric current in this coil, right, it starts to heat up. You can feel the heat coming off it before you see it glow. Well, that's infrared radiation, isn't it? You can't see it with our eyeballs, but we can measure its energy. And then it goes into the visible range. Starts out a very dull red, goes to orange. All stoves, annoyingly, have these things called governors on them that prevent you from turning them up high enough to where these melt. Right? But if you could keep turning up the current and giving more and more energy, it would turn yellow, and then it would turn blue, and eventually it would turn white. And why would it turn white? All the visible wavelengths of light are being given off now, right? There's enough energy there. And then, of course, it would melt long before it got white hot, right? But if we could keep heating it up, it would start putting the ultraviolet off, and then X-rays, and then gamma. Like a pure black body gives off everything, right? But you can't do that without some serious consequences. Sun doesn't even really do that. So Planck is using the next best thing, which is a really hot oven. He can very precisely tune the temperature up. He's got a little pinhole through which he's like observing the frequencies of light that are inside that oven. And what he's trying to do is he's trying to find a relationship between the frequency, the color of light that's coming out of his oven. Again, you can go through infrared and then the very dull reds and then yellow, right? You keep heating it up all the way to white hot. He's trying to find a connection between the frequency of the light that's being given off and its energy. And no matter what he does, he can't get it to work. Okay? So he's looking at these different temperatures. He's looking at the intensity of light. This chart right here is trying to show you that within the visible portion of the spectrum, we expect at certain temperatures to have different peaks at where these wavelengths and hence the frequencies are. But more to the point, okay, this curve, right, doesn't fit the classical theory for how energy and frequency work. That red curve, the red-brown one there, is what you would calculate if you were using, say, Maxwell's equations to try to figure out what the energy of the waves are coming off of these black bodies. But it's the blue curve that marks Planck's experimental data. And so there's this discrepancy, right, between what Planck is measuring and what is theorized or being calculated according to classical physics. And so Planck assumes, every good experimentalist assumes this, that our experiment is wrong. Maybe it's because the theorists bully us or something, but we just always assume that we're, right, if theory says this, experiment says, well, then maybe the experiment's wrong. And so he kept trying different things, and he always came up with the same thing. And that right there, if an experimentalist keeps coming up with the same thing after changing lots of stuff, that's the point where you go tell the theorists that they're wrong. Right? Something else is going on. But Planck is like, and no matter what he does, he can't get away from a very simple relationship. Okay, one that's kind of these charts make it look more complicated, but basically what Planck discovers. I hate technology. I know, the screen died again. That's all right. This was not all that important.
Comes back.
Well, I know it comes, and as soon as I hit this, it's going to go away again. So, it's a software issue, okay? But even people on YouTube can know E equals HF. I don't really need to draw that on the screen, okay? So the energy that Planck is measuring coming off of his black body in his lab is equal to the frequency. There's a relationship there times this thing that would later become known as Planck's constant. It's a constant that's sitting out in front of there. And so what Planck has done is he's measuring. He's measuring something he doesn't want to measure. He's like, I don't want it to be this way, because what Planck is trying to do is establish that there is a wheelchair ramp of relationship between energy and frequency. A wheelchair ramp is designed so that there are no abrupt changes in potential energy as you go up the ramp. It's a nice, smooth, connected experience. Makes it much easier for a round wheel to go up the ramp, right? Stairs, on the other hand, don't do that. Stairs require abrupt changes in gravitational potential energy. The potential energy of one step suddenly changes to the potential energy of the next step. And then if they're wide steps, you stay at the same energy for a while before you go up to the next one, right? Okay? Planck wants to find the wheelchair ramp of energy and frequency. He wants a nice, smooth connection from infinite number, right, of grades of change. What he's finding is the staircase. That's what this equation is. He's discovered that the energy is always coming off in these discrete chunks, and that the smallest energy you can ever get out is equal to this constant times the frequency. So really, the total energy coming off of his black body is always an integer multiple n, right? Like what Planck has discovered is that energy is quantized. It's not smooth, it's not infinite equation. There is a lower limit on the amount of energy that can come off of this black body. And he publishes this, and then he shelves it as an interesting curiosity. Like, he even in his papers, like, mistakes have been made, I'm not sure what they are, I'm hoping the scientific community can figure it out. And then nobody does. And it kind of gets forgotten for 2 years. Do you remember that we started with what is light? We've just spent the last week and a half talking about what this guy thought light was. But I didn't talk about this in the context of the lecture I gave on the history of light, where we started with Newton. Newton thought light was a particle. And then Thomas Young came along and showed us that light was a wave. And then black and white photography came along and showed us that light was a particle. And then Maxwell came along and showed us that light was a wave. What does Albert Einstein think? Well, any man who, in response to a photographer saying, "Hey, professor, give us a face," would give you this one. This is actual picture. This isn't like AI generated or anything like that. Real picture. He really did this. Okay? Must have an opinion. remember that there were 4 papers in 1905? Do you remember what they were? So special relativity takes up 2. There's one on Brownian motion that we're not really talking about. It showed to the scientific community that atoms truly, really exist. It was like the final nail in the coffin of any other idea. Atoms are real. Okay? So Albert Einstein, atoms are real. Remember what the 4th one was? Photoelectric effect. What is the photoelectric effect? Let me show you in a video. Nope. Just kidding. Why didn't that play?
And the evidence can still be seen today in the behavior of a gold leaf electroscope. When the electroscope is charged, the leaf rises and stays aloft until it's hit by a beam of ultraviolet light. An ordinary piece of glass transmits visible light, but it blocks the high-frequency ultraviolet light. When it's interposed, the electroscope doesn't discharge. But when the glass is removed, the leaf falls again. This proves that the ultraviolet light does the job, and it's called the photoelectric effect.
Did that help? No. It's a physics experiment. Needs explanation. This is how I get job security. What did you just see?
They went up and then went down again.
Okay. We're discharging metal using what? Light. Okay, full stop. Did you know that you could discharge metals using light? Probably not. Okay. Now you know. You shine light on metal, charges will leap off. But it has to be the right kind of light. In this video, what was the right kind of light? Ultraviolet. Visible wouldn't discharge the electroscope, but ultraviolet will. That is the photoelectric effect. The photoelectric effect is the discharge of metals when they are exposed to certain frequencies of light. We're going to talk a lot more about this on Wednesday. Okay? But I'm starting you off baby steps right now.
Does this relate to photovoltaic in any way?
Yes.
So Newton basically, not Newton, Einstein basically got us on the first path to solar panels.
Yes. Because solar panels are quantum mechanics. All right, but we're getting ahead of ourselves. Photoelectric effect. Einstein writes a paper on the photoelectric effect in 1905. Einstein wins a Nobel Prize for one of the 4 1905 papers. Do you want to guess which one it is?
Brownian.
It's for the photoelectric effect. Okay. Why? I mean, Nobel Prizes ostensibly are given out for what?
Outstanding achievement.
Outstanding achievement, work that forwards our understanding of the universe, medicine, peace, literature, whatever, right? Okay? 4 papers to choose from. The Nobel Committee chooses that one. What does that tell you?
They didn't think special.
They didn't understand relativity. Okay, number 1. And number 2, of the 2 that were left, right? By then, his general relativity, of course, has happened. Albert Einstein would win the 1920 Nobel Prize for photoelectric effect, not for relativity. The thing he's famous for, he did not win the Nobel Prize for. Okay? He was awarded the prize in 1921. There was no Nobel Prize given in 1920 for physics. The reason being is that the Nobel Committee couldn't decide. And so in 1921, they offered 2. The 1920 prize to Albert Einstein and the 1921 prize to, I can't remember who, doesn't matter. The Nobel Prizes, the committee's deliberations are always confidential. never released to the public. We don't know how they choose, why they choose, whatever they choose. Based on interviews that were conducted much later in their lives by the people that sat on that committee, there is excellent evidence that Albert Einstein was not given the Nobel Prize in 1920 because he was a Jew. New committee was formed in 1921, less racist one, and they managed to award the prize. So there is some discrepancy over maybe which Nobel Prize he should have won. Based on popular opinion, it should have been relativity, but it was for the photoelectric effect was the most politically neutral one to give. But racism or not, and I'm not condoning racism at all, but racism or not, it would turn out to be that the photoelectric effect paper was the more important one. Even more important than completely rewriting our understanding of the universe? Absolutely. Because the photoelectric effect firmly and unequivocally establishes that light is a particle. The photoelectric effect can only be explained. The discharge of metals by light can only be explained by assuming that light is a particle.
Because electricity needs to be getting to travel through.
If you use Maxwell's equations, you cannot explain the photoelectric effect. What is going on? In Maxwell's equations, in our wave formulation of light, the energy of that light is carried in the amplitude of the wave. To make light brighter, to give it more energy, you simply change the amplitude of the wave, leaving the frequency and the wavelength unchanged. Albert Einstein realizes that he needs an equation in order to figure out what the energy of a particle of light would be. Turns out Max Planck had already found it. Max Planck didn't know what his equation meant, what his laboratory experiments meant, why he kept getting this staircase. Albert Einstein digs out his paper and realizes what Planck has found. Planck has discovered the photon. And Albert Einstein is able to explain the photoelectric effect the following way. The energy of a particle of light, a photon, is directly related to its frequency. The higher the frequency, the more energy the photon has. Light, visible light, being lower in frequency than ultraviolet light, does not carry sufficient energy to knock the charges off of the material. But ultraviolet light, with its higher frequency, does have sufficient energy per photon to knock the charges off the metal. You cannot explain the photoelectric effect using wave mechanics. You have to use particles. This is called the Planck-Einstein relationship for the energy of a photon. Planck's constant, annoyingly, is a number. That's not the annoying part. I mean, numbers are annoying. 6.63 times 10, I always have to check because I never believe it, to the minus 34 joule seconds, not joules per second, joule times seconds. to any self-respecting physicist, what is that number? That's 0. Right? I mean, come on! 10 to the minus 34? Are you kidding me? I'm not kidding you. This ends up being hugely significant. And we're going to untangle that significance. We've got 2 freight trains that are barreling straight towards each other. We have James Clerk Maxwell on one train, and we've got Albert Einstein on the other. Wave, particle, and they're on a collision course. What's going to come out of the train wreck is called quantum mechanics. And we'll pick that up on Wednesday. Tomorrow, I'm joking, bring your tennis shoes. We're going to do a lab on relativity. I'm going to need you to run it near, close to the speed of light, not quite the speed of light. Okay? So there'll be some unintended weight gain in lab. And lab is going to last a long time. You'll be moving so fast, the time will be dilated. No. Come to lab tomorrow because you are going to practice relativity. You need this practice. See you tomorrow.
What's your